Everyone, this is the presentation of performance of an air radiative system in a residential building in Chile. This presentation is organized. I will start with materials. I will continue with experimental results and discussion, and I will finish with conclusions. So, we test an air radiative system in a residential building in Chile, in specific in Valparaiso, which is a coastal city. So we use a prototype that is called a Casa Feni that you can see on the picture. The system is composed by an air collector and a wall pack bed, which is inside of the house. So the incoming air is cooled down because radiative cooling exposed during the night, and this cool air is passed through the pack bed, and the pack bed is cooled down during the night. The idea is to accumulate cool energy on the pack bed during the night because of the radiative cooling with the sky, and reduce the thermal load during the day, reducing the thermal load that it needs to be against the air conditioning, for example. So we use an air radiator that it has 2 square meters of surface area that is well insulated, and it has an aluminum plate with an emissivity of around 88%, and it is installed on the roof of the house. So we have measured the ambient condition of the 2 days that we have measurements. So and we can see that the temperature is around 10 degrees during the night. The relative humidity is high because we are in a coastal place. It's not the best place for radiative cooling, but and also in that place the wind speed is really low. So we can see on the air radiator performance measurement that we can see a really cooling effect if we see the dashed line, the solid line, and the cross line. The dashed line is the inlet temperature, the solid line is the outlet temperature, and the cross line is the plate temperature. If we plot the difference for these 2 days, we can see that in the worst case, we have around 2 degrees of cooling and 4 degrees of cooling in the best day. We have developed an analytical model that involves the energy balance for the system that has the internal convection, the net radiation, and the external convection. The net radiation is explained because the interaction between the panel and the sky, and the sky requires to know the sky temperature, and we use for that purpose a well-known correlation. The dew point also is obtained from a correlation that is here. If we see the cooling power, we can see that the worst day we get around 25 watts and the best day around 60. Also, we can identify the contribution of the net radiation, that is the circle, and the external convection, that is the cross. Yeah? So here, at this moment, it's not clear why we have a better cooling power at this condition. One explanation may be that because we have a higher air mass flow rate, we have a higher heat transfer coefficient, and it can provide this higher cooling power. But this is not the only reason. Also, it could be affected because ambient temperature, and also it could be because cloudy conditions. So we need to explore and research even more. So We will continue with our research, but we have our first conclusions. So we believe that it's possible to apply this technique in Chile. Yeah, we have measured some cooling power even in an unfavorable coastal Chilean climate. Yeah, so this result should be better if we move to other Chilean climates that are hot and arid. About the air system, so the air collector could be improved using a selective material on the plate, also adding some wind shields, and also the design could be improved adding fins and deflectors. On the coupling with the indoor wall pack bed, we need to take special care with the design because the interaction between the thermal unit and the indoor conditions. The use of control test cells will surely help in the comprehensive approach of this complex. That's all. Thank you for hearing.